After that, Sir was awarded Humboldt Fellowship, the prestigious Humboldt Fellowship, to work in the research group of Professor Henninghoff at Technical University of Braunschweig, Germany. And later, he also received Australian Research Council Discovery Grant Fellowship with Professor Martin Banwell at Australian National University, Canberra. And in 2001, he returned to India, being awarded with Ramanujan Fellowship by SERB DST, and he worked at Indian Institute of Chemical Technology, Hyderabad. And then he took up a position at the Central University of Haryana in 2017 as an assistant professor, where he received the Best Researcher Award in 2018. And in 2022, Sir was appointed as the professor at Department of Chemistry, University of Calicut. And his research area includes general organic synthesis with specific interest in unsaturated sulfones and benzanylation reactions. And Sir has published more than 50 publications. And with that, I invite Sir for the session.
Thank you, Dr. Deepthi. I hope I am audible. Pradeep sir, organizers of EFCS, thank you for giving me this opportunity. This conference has already created a legacy, and it's really proud and honored to be a part of this. And thank you for keeping a old picture of a younger me in the slide. I'm going to talk about organic synthesis, and that means a lot of reactions and their details. And you will not see any immediate applications for what I'm going to tell you, but you must have seen its relevance in yesterday's lecture by Dr. Nandakumar. And I could see from some of the questions in the last night's interaction that Nandakumar has ignited something in many of your minds. What I'm talking about is a pharmaceutical industry. The big, beautiful, glamorous edifice of pharmaceutical industry is built on the foundations of organic synthesis. So that's like a sales pitch for what I'm going to tell you. And I'm going to talk about sulfones. Why sulfones? Let me start with this quotation of a famous senior organic chemist called Philip Fuchs. There is a name reaction after him, Corey-Fuchs reaction, a very senior respected figure. And this quotation is from a review, chemical review articles that he wrote in 2009. It says, phenyl sulfone is arguably the most versatile functional group available to the synthetic organic chemist. Look at the phrase, the most versatile functional group. When we are taught in classrooms, and some of us teach, that carbonyl group is the backbone of organic chemistry, and I firmly believe so. And here is a senior figure saying the most versatile functional group is sulfone, which is not even a mainstream functional group. Non-specialist organic chemist may ask, what is sulfone? Is it SO, SO2? Because it's not that popular. So why I selected such a functional group? Part of the reason is in that statement. That's a tall claim to make. I will not make that claim. And if you contest that claim, you are happy to go and argue with this formidable-looking professor. But there are some properties of sulfones that are very, very unique. One is shown here in the form of an equilibrium. Vinyl sulfones, sulfones that has a double bond adjacent to it, and that has some gamma hydrogens present. If you treat that with a base, it equilibrates. This hydrogen has some acidity, and base can deprotonate it, and it isomerizes to an allyl sulfone. And this equilibrium lies to the right. And this is very unusual. Generally, systems like to move into, double bonds likes to move into conjugation and become more stable. Here, already conjugated double bond, conjugated to SO double bonds, moves away from it. And the allyl sulfone has a better stability. It is thermodynamically more stable. It is proven experimentally many times. Little is known about the reasons. And the sulfone part can actually leave. It can behave like a leaving group. And in fact, it is 1,000 times better than a chloride ion. in its leaving group ability. So these are unusual properties of a conjugating functional group that is not present in other common mainstream functional groups that you generally encounter in organic chemistry. Not only that, sulfones are present as a group in many drugs. A famous example is dapsone. This was very important in the treatment of leprosy some time back. Now we have better drugs, but in my childhood I used to see people who are affected with leprosy. Now we don't see them in public. So this was possible by large availability of this drug. Not only that, sulfones make compounds very stable, crystalline, and it's easy to handle. Organic chemists love this. Now, most of the chemistry that we have done depends on this unusual feature. We will see why this is very important and useful. So one of the class of compounds that I'm going to talk about, or I have used, is a sulfone which is having an allene attached to it, which can be called allynyl sulfones. These are not available. They are proven to be quite unstable, difficult to handle. You can make it, use them, but it's not as easy to handle as a analogous compound where you have an allene and an ester attached to it, generally known as allynoate. These allynoates are very popular. There is a lot of literature on its reactions, especially nucleophilic catalysis of allynoates. You add a nucleophile, it can transform into a very reactive intermediate and give you different sort of reactions. Now, why not you see enough chemistry on allynyl sulfone? The reasons are here. So we found a way to circumvent this. How? We can make allynyl sulfone in 2 steps, starting from a simple allyl bromide, 2,3-dibromopropene. This is available from chemical suppliers. Treat that with a sulfinate salt. This is how sulfones are made. The sulfinate salt is a sulfur nucleophile. It displaces the aliphatic bromine. You get a bromosulfone. Treat that with a base. You can eject 1 molecule of HBr, a simple elimination reaction, which should give you an allynyl sulfone. And these compounds are very stable, crystalline. You can make it in large amount and keep it, no problems of stability that are associated with allynyl sulfones. And what we found was you don't have to make the allene to do its chemistry. Instead, you take the allyl bromosulfone, treat it with a base. This is the best combination that works, cesium carbonate in acetonitrile. Allene is formed, but if you do this reaction in the presence of a nucleophile that's generated by deprotonation of something by the same base, and this nucleophile adds to this electron deficient allene. That's very common classical chemistry, but here there is a twist here. This nucleophile can be phenols, sulfonamides, carboxylic acids, active methylene compounds. These things are acidic and deprotonated by cesium carbonate. What is the twist here? The twist is this. Let us look at a similar reaction of an allynoate. If you do this reaction with an allynoate, this Michael addition, heteromichael addition, a nucleophile would add to this central carbon. You will generate an intermediate carbanion, which is stabilized by this electron withdrawing group, and that will be protonated. And when that protonation happens, invariably you will get a protonation at this end. This double bond will be moving into conjugation with the carbonyl group because that is more stable. And you will get a product with a double bond which is between this is nitrogen, this nucleophile is nitrogen. So electron donating and electron withdrawing group, a push-pull system basically. Electronically it has no definite character. It's neither rich in electrons nor electron deficient. And it is buried between 3 substituents. So there is very little that you can do with that product. Whereas, if you have a sulfone here, the protonation leads to a product where the double bond is away from sulfone group. The reason I have told you earlier that allyl sulfones are generally more stable than vinyl sulfones. So this product is completely different from the product shown here. because it has a very electron-rich double bond, di-substituted. It's ready to react as a nucleophile with suitable electrophiles. You can do a lot of things about it. So exactly this is the feature that we have utilized in all the chemistry that's going to follow. It's a very simple fact that allyl sulfones are more stable has allowed us to divert the chemistry of heteromichael additions in different directions. Now you will see a lot of reactions, but remember, underneath all that complex reactions, this simple principle is the guiding force that has allowed us to go in different directions. So what have we done? In a quick summary, you can look at here, the bromo-allyl sulfone treated with base and different nucleophiles, you get a substitution of the bromide. So if you look at that reaction, the starting material and the product, you will see that it's equivalent to a vinylic substitution. You know that nucleophilic substitution, SN2 substitution, cannot be done on double bonds. It's not possible. Probably the reason must have been discussed in your classrooms. But this is what we are achieving. But it is not a substitution. It is an elimination followed by Michael addition. So we call it a formal vinylic substitution. But generally such chemistry is done with the use of palladium catalysts like Buchwald coupling. When you have a vinyl bromide, you want to form a nitrogen carbon bond, you have to use palladium, copper, or some other transition metal catalyst. Here we don't need anything like that. Simple base, simple conditions, you can do it in a bucket. So these are reactions that would attract the attention of industry, that can be scaled up easily without having any very highly sensitive conditions. So this is, now we usually call it a formal vinylic substitution so that it's, sounds nice. Now what have we done with it? Now we can have different nucleophiles. A nucleophile, a sulfonamide that already carries a functional group like an acetylene. It can be attached to the bromosulfone to give you this vinylic substitution product. And that, as I said earlier, this double bond, the red one, is very nucleophilic, very electron rich, which can be made to react with this alkyne. All you need to do is activate that alkyne, make it electron deficient by pulling its electron density using a catalyst that likes alkynes a lot, for example, gold. And the reactions can go in different directions depending upon the catalytic combination. You have nice divergent pathways to either make pyrroles or dihydropyridines. The reaction is not a simple cyclization actually, because if you look at this 3 red carbons, 1, 2, 3 carbon fragment, you can see that they have undergone some rearrangement. And that is shown here in the mechanism. The first step is, as we discussed, formation of allyl sulfone, formation of deprotonation of the sulfonamide, addition of the nucleophile to here, and then you have a propargyl Claisen rearrangement mediated by the metal, gold and silver, and you get a allyl-imine which can cyclize in 2 different ways, either through a 1,3 hydrogen shift and a 6-pi electrocyclization to the pyridine, dihydropyridine, or a 5-exo decyclization. The nitrogen directly adds to the central carbon here to give you a 5-membered ring. You can extend this, once you have this, blueprint of a reaction worked out, you can play around by setting up functional groups. For example, here, we have a different nucleophile, an orthoiodo sulfonamide, and you do the vinylic substitution, then do a coupling, Sonogashira coupling, to install an alkyne here. Now this part survives the Sonogashira coupling, it's very stable. And then you treat it with the gold, then you get a very nice, completely selective 7-endo dig cyclizations. A 7-member ring is formed, which is not easy to form. And you get benzoazepine's, which are very important scaffolds for medicinal chemists. There are not many methods available for their synthesis. Again, as I told you earlier, you can set up cascade reactions. So this is the assembly of the starting material. Here we have 2 alkynes, one here and another here. and you set up stage-wise cyclization, same catalyst, one cyclization, you get a pyridine, and this double bond is again electron-rich by virtue of its conjugation with this nitrogen lone pair. So you can cyclize this again in a 6-endo mode. You are installing 3 rings in the same step. So from a fairly simple starting material, you are going to a complex product quickly. We can also do very simple anionic basic chemistry by exploiting these reactions. You take a nucleophile, phenol, which already has a hidden, not a hidden, but a very visible electrophile present in the ortho position, and do the allynyl sulfone chemistry. The intermediate anion can cyclize, and the product that we isolate is actually an isomerized one, not this adduct, but an elimination of water and an addition of water has happened. Now, the beauty of this molecule is that it immediately, it has a tendency to become a benzopyrrhelium cation. It's aromatic and it's stable. And in fact, this cation is behind the color that you see out there when it is autumn. All the leaves become yellowish, orange. That different colors that you see in nature is mostly coming from anthocyanins. That has a central structure like this. It's very stable. That's why it's seen in nature a lot. So that stability is reflected here. It's very easy to make this. We don't isolate this, but we are speculating that it is formed because that can be trapped by nucleophiles very easily. Very high yielding reactions, very simple chemistry, but from very simple building blocks available in the shelf, you are going to fairly complex and decorated molecules that would generally attract pharma chemists. So to extend this further, we have used gold chemistry, we have used now palladium chemistry. You use the iodo sulfonamide, do the same formal vinylic substitution, and then utilize this iodide in palladium-mediated cyclizations. Here we see some nice selectivity. If you have the sulfone group R is equal to methyl. If it's a methane sulfonamide, you get this isomer. If it's an aromatic sulfonamide, you get a different isomer. Similar trends are seen in phenol. You get both. And this sulfonamide gives only one product. Here, only one type of isomer is formed. This selectivity, I think I have probably missed the slide on this reason for selectivity, which can be explained on the basis of steric. But I will tell you a little bit detail about this story. This is something that we did not expect, but led us to a very interesting observation. So what we were interested in was the synthesis of a family of alkaloids called sub-incanidins. These are relatively new alkaloids which have shown very good anti-cancer activity, isolated less than 10 years ago. So this sub-incanidin family of alkaloids have this skeleton of a tetrahydrocarbolene, that is the indole plus one more 6-membered nitrogen heterocycle. So we identified that we can make this tetrahydrocarbolene very quickly using our chemistry. You take a tryptamine sulfonamide, do the formal vinylic substitution. You have an electron-rich double bond here, protonate that with an acid. So you will get a cation here that can cyclize with the indole. That is what you expect. And we have handles for growing the rest of this natural product. So we thought we will get this, tried this reaction, protected sulfonamide with a protected tryptamine as a sulfonamide, did our chemistry, works very nicely. You can have different R groups here and different aromatic sulfones. And when we tried the acid-mediated cyclization, we got this product, expected product, but only when this is a methyl. And if this group on the sulfone is an aromatic group, the product that we obtained had a 7-membered ring. So obviously this 3-carbon unit has detached and rearranged somehow and cyclized. So we were looking to go here, but we have now a route to go either here or here. Now the interesting point here is the mechanism. I will just quickly go through this, and this is what organic chemists like to do. And this is important because it might appear boring to other chemists, but if you want to do something to a reaction, you have to optimize it, tweak it. You need to know this. You need to know about the intermediates, how to stabilize them, how to divert the reaction, etc. So what happens here is, as we speculated earlier, the double bond is electron rich. It's like an enamine, it gets protonated on carbon, and the corresponding carbocation, or its resonance form is shown here, is cyclized from the electron rich indole epictet Spengler type cyclization. You get this product. And this is isolable when this group is methyl. But if this is a bigger group, probably there is a steric problem with its stability, and a slow protonation of the sulfonamide nitrogen can relieve that steric interactions by forming this cation. This cation, once the CN bond breaks, this is a cation that is formed. The cation is not bad. It's stabilized, it's tertiary, it has Benzelic type of stabilization from indole. And this cation can lose a proton from the methyl group to give you this alkene. Now, if this alkene is protonated and the nitrogen cyclizes, you will go back. But there is another possibility. The indole can be protonated on the 3 position. If that happens, all these equilibria must be existing in this reaction. If indole 3 protonation happens, then you have an iminium ion like this, which is conjugated. You have, in fact, inverted the polarity of this double bond for a nucleophilic attack at this end, and then the rest is a simple tautomerization to give you this product. And this reaction does not work with benzene rings here, because there is no indole for a 3 protonation. So obviously it will not work. Now, Now this, if you look at the mechanism, you can see that I was taking sulfones all the way up to here. Now I am going to become a little bit thankless and say sulfone is doing nothing here in this rearrangement. It's a spectator, you can see. You don't see any role for the sulfone. If this mechanism is true, you don't need it. So then, if you don't need it, why don't we try that? You take simple tryptamine, make a tetrahydrocarbolene ring by using conventional chemistry. And in fact, this conventional chemistry was not very known. When we looked at it, very few conditions were available. We had to do some tweaking of our own to reach here. It's basically an imine formation and a pictet Spengler cyclization, then tosylation. Then you treat this with the tetrahydrocarbolene, which does not have a sulfone. Same conditions, the rearrangement still happens. So our speculation was right, sulfone was not doing anything in this particular rearrangement. That means this is a general reaction. So if it is a general reaction, we did that with many examples and we could isolate this product in many cases. But in some cases, we isolated this alkene. And that is not a surprise because in the mechanism that alkene is an intermediate. So the mechanism is analogous to what we have seen earlier. Protonation of the nitrogen, opening of the ring, a cation. Cation is stabilized to form an alkene. So this is a stable product. In some cases, we can isolate it. It's not a surprise. And in some cases, it goes on. Where the kinetics and conditions match, probably it goes on to the next cyclization event. And that is actually an anti-Markovnikov addition on this alkene, which is only possible because of indole's interference in it. So this is why mechanism is important. When you have to explain and rationalize this unusual addition, anti-Markovnikov addition, which looks, on the first look, it looks unusual, but when you look at actually this, it's nothing unusual about it. And the rest is some tautomerization. This is an enamine becomes imine, and then the next enamine is aromatic indole, so that is the product that we isolate. Why am I so excited about it? Because nature is rife with indole alkaloids. We have indole tetrahydrocarbolene alkaloids, many. The list goes on. Some famous ones are shown here. Reserpine and the subincannidines I just mentioned. Nature also has indoloazepine alkaloids. Not that popular, like not that widespread as these ones, but they are there. So now, if you open a biochemistry textbook and look at the biosynthesis of these alkaloids, these are 2 different pathways. These alkaloids are formed in one pathway, and a totally unrelated pathway is proposed for the biosynthesis of these alkaloids. Now we have a general conversion that shows these systems can undergo rearrangement to form a 7-membered ring just by a mild acid. So it can possibly happen in physiological conditions also. So if this postulate is correct, we can probably think about editing some biochemistry textbooks in the future. And this is just a summary of what we have done with this small building block. You can see the complexity of the products. From here, it's only 2 or 3 steps to this. And that's all possible because of this little guy, sulfone, which allows us to do such chemistry. And this is the wonderful team that has done this work. Some of this work was done in Haryana when I was in Central University of Haryana. And right now we have a team of these lovely people here. And one of them is a donation from Farook College, and he's also named Farook. And so that's another reason for being here with a little bit of thankfulness. And thank you for listening to me.
The synthetic applications of sulfones. Now the session is open for discussion.
I cannot possibly ask you an intelligent question on organic chemistry, but let me make one comment to you. You are sitting there as the head of the department.
Yes.
And you talked about anthocyanin and possibility of looking at intermediates, possibly studying a variety of possible structures which are relevant to nature. And because of our diverse biodiversity and lots of interesting things here, I wanted to make the suggestion that there is this mass spectrometric technique called desorption electrospray, which can directly detect molecules of this kind from plants and surfaces, tissues, and all that. And I know that I was once involved in that kind of a study to see how an autumn leaf transforms. And I wanted to see whether such studies, if you were to incorporate, you would be directly connecting nature with your laboratory,
right,
and will be a unique way to contribute to the region.
Right. So, yeah, Jan, we organic chemists do it the hard way. Pluck all the leaves, grind it, take the paste out, extract it, take the spectrum. Now we have a better technique, so it will be much easier to detect.
It is extremely rapid and very highly surface sensitive. And it can be used for imaging, so you can get a photograph of the leaf with molecules.
Right. Thank you, sir.
Excellent piece of work, I must say.
Thank you.
Quite interesting to see that rearrangement. Just had one question. I noticed that you were using trifluoroacetic acid in one of the steps prior to that.
Paratoluene sulfonic acid.
No.
Which
go
one?
back a couple of slides. Right
yeah,
there.
this one. Yeah, here. Yes.
So after you do the thing, you do the pictets, the titanium isopropoxide, I think, forms the
tetrahydrocarboline, NH.
Well, yeah, it forms the imine, the titanium isopropoxide. Then you cyclize with TFA.
Right.
Right?
Yes.
So, if it's an amine, it does not cyclize. Is that correct? And then when you put the tosylate on...
No. The imine is formed first in the first step, as you said. Titanium isopropoxide is a dehydrating agent. Then you treat it with acid, trifluoroacetic acid. Then it cyclizes, the pictet spengler. Right. Then you get a tetrahydrocarboline with the NH.
Right.
And we try to rearrange the NH because the nitrogen protonation should be better there. Doesn't rearrange. The N-tosyl, and if you try to put very bulky groups here, it doesn't work. This is already next to a quaternary carbon. So tosyl goes there, very slow reaction, and you need a tosyl there for this rearrangement to work. Bock doesn't work. It's very sensitive to the conditions, substituents. And conditions are very mild, 25 degrees, a mild acid. But if you have something else here, see, even phenylsulfonyl, it stops here. Tosyl, it goes all the way around. And you treat this further, doesn't convert. Like in the previous case, it was very nice, smooth conversion. So this story is unfinished, still going on. But we have shown the feasibility of that rearrangement, somewhat general. So could happen in nature, because nature does not need a very efficient reaction. It can, it has its own way of optimizing it to using a particular catalyst, we call enzymes, right? So if it is feasible like this in the lab, there is a possibility that nature is also doing this. And we can test it by taking this 6-membered alkaloids and then trying out acid-mediated conversions, whether you are forming at least some amount of the 7-membered ones. So that's something we want to do in future.
Second question is this specific to tosic acid? Is this specific to tosic acid, or can you just use HCl?
No, HCl just destroys the whole thing. It works with similar acids like trifluoroacetic acid is effective. Camphor sulfonic acid also does this. We tried a chiral phosphoric acid, a chiral, that binol type acid. It doesn't work. It has much lesser acidity than pyratoluene sulfonic acid actually. We need to find a chiral acid that is having a similar matching acidity. So that's all part of what's going on now. So it's sort of, I'm excited about it, but I'm not in a position to fully give you what's really going to happen.
Thanks.
Thank you.